roll on to the time, then I can add my thing or something like that.
Okay, I'll just present. Which is this one? All right. So last week we were looking at this revised support vector machine model dimensions of the hypersphere. I think you recall. So I did my best to go over this, and it was a bit difficult, to be quite honest with you. So if I run this, and I think so the trouble was, remember I was like, oh yeah, we got it right. Well, I don't think we did get it right in the end, because I went back and here is the we were trying to inscribe the points of the hypersphere on the points of the hypercube onto the hypersphere. So that would be this. Then we had to multiply it by 70 because that was a scaling factor, and that gives us these coordinate points on the sphere. Then we reproject back, and we see that the points are right here. There's one orange point, another one, another one, and another one. So that's quite far out. We can zoom in, and it's definitely just one point. So those are the 4 points there. So the other 4 points are, this seems to say -1/2 infinity, 1/2 infinity. So we're talking about something that's, if these points are -1/2, which they are, and +1/2, then the other point at the other group of points at the far side of the universe are basically infinity -1/2, or +1/2, which is obviously not a number that we can work with. So this is the same thing here, basically, although, yeah, we've put this number in, and it's that number just from here. Yeah, it is. So it's the same number, and we get the same results. And so if we zoom in on this, we see that our cube is actually quite, this is the 3-dimensional version now, yeah, is quite close into the center of the block of the spheres. So the Earth would be at the center of that cube, and then, so that's nice. So if we were saying that this was the size of the little cube, then great, we could work out the size of the bigger cube and the actual size of the hypersphere from a 4-dimensional perspective. But we have the same problem here, because these are at -1/2 and +1/2. See what I mean? And so the larger sphere, the larger hypercube vertices will be at infinity -1/2. So as I said before, we cannot use these results. So
These are not inverted, right? It's not inverted, right? It's not inverted cube. It's the real inscribed cube. Inscribed cube within the sphere.
Okay, so let's go back to our results. So, or maybe I don't need to open that. So my thinking is this. I think that our interpretation of this data is possibly wrong. My original interpretation. Let's imagine that this is the hypersphere boundary, the red line, red circle. And well, what it actually is the decision boundary between the support vector machine analysis, between the two classes that we have here. And so I was thinking about it, and I was like, well, beforehand we said that this whatever radius from the center out to this circle was the radius of the hypersphere, yeah, or one of the projected radiuses. But upon thinking more, I think since it's meant to be a decision boundary, perhaps it should be halfway between the two different. Is it the two transformed hyperspheres? Or yeah. So if by transforming everything it goes inside one sphere, and transforming it the other way means it goes outside, then perhaps the decision plane boundary is kind of sitting in between the two, which would mean that the actual radius is twice the size of the decision boundary. And then when we work out the mathematics for that, so instead of 43.2, it's 86.4. And then when we divide by 3, we get 28.8 megaparsecs for the radius. So this alters everything that we had done before, or, you know, all the work I did on the hyperspheric dimensions, because now instead of a radius of, what is it, 14.8, 14.4, sorry, we have, the radius is now twice the size, it's 28.8, sorry. So here are the redone metrics, I think. Radius, hang on a sec, I'll just sort. So the radius, 28.8 megaparsecs. So the diameter will be 57.6 megaparsecs. So the circumference is 180 megaparsecs squared. And the surface area is 471 gigaparsecs cubed. The volume is 3.3949999 teraparsecs to the fourth. We can also work out if the circumference of the hypersphere is rotating once a year, then that works out at 590 million times the speed of light. That's how quickly it rotates. But that's only at the circumference. Obviously, at the poles there is no rotation, so it's zero speed of light, which is, we're at one of the poles, so this speed doesn't really affect us. So that's it. So that was my my attempt at solving that kind of thing. Because of the changes then to the radius, as I said before, that kind of changes everything that we've done prior to this. So I had to update some of the older work to see what the results would be. That's just the scaling factor of the universe in the first day. And we see that the average of the scaling factor is 28.8, which again is, it now appears to be the radius. So we have, this is the growth rate of the universe. So now this is the pressure differential, and we notice that it's, oh, I'm not sure if I like that. It seems to be different to what I had earlier. Sorry about this. Just run it again. Yeah, I don't know. I may have made a mistake because, well, yeah, I don't know. I'm wondering how many of these values will turn out differently now that are, that's the same. Skip that, I believe. No, we don't. Skip that. We need this. Interpolate, did it? Okay, I think that's all right. What is interpolate? Okay. Surface area, that's all right. I don't think any change happened there.
Usually, interpolation gives a fairly good answer. Extrapolation may not give correct answer. That's usual thumb rule. Yeah,
that is true. Yeah, we've got now we're going to extrapolate.
So that could, it depends on the linearity, non-linearity. The extrapolation a lot of times can give spurious results.
That's fair. I'm not entirely sure. Okay, everything seems to be going well. Oh, now I think those values changed, did they? I'm not sure. That value changed, but maybe that's not too important. Maybe I'm in the wrong.
You're talking about ordinary space, dark space.
Maybe I'm in the wrong notebook. I don't think I am. Maybe I am. Oh, maybe I was. Don't know what happened there. That was a bit odd. Okay, I was in the wrong notebook. So there we have the scaling factor. Just hide that and go back. Right. So this is the pressure differential from the inside of the hypersphere to the outside of the hypersphere, and we notice e to the minus 34, which is, so these values here, one of them should be fairly close to the Planck scale. Do you know the Planck scale off the top of your head?
Planck scale, yeah, 6 to the power negative, 10 to the power negative 34 is the Planck constant.
Okay. So technically, anyway, this is a pressure differential. So, but it's kind of in the realm of the Planck, but it's not
H bar. Probably H bar.
Maybe. Yeah, that's a good point. I mean, yeah, we'll look into that. Don't think we need that figure. So there it is, printed out. Absolute pressure from the gender transform. I think we can go with that. So this is the surface area expansion in terms of kilometers, and we can plot that. Just ignore the red trace on that one, and then we can do the same with not the surface area this time, but the volume. And now we can do the Legendre transform for the surface area, just for a single dimension. We get this. If we do it for all 3 dimensions of space, we get this, which is a much more sharper, steeper curve. So this is the expansion of the surface area. It says volume there, but ignore that. But you could say 3D volumetric. And then this is the pressure. As it expands, it drops like that. Now we do the same thing for the volume of the hypersphere in a single dimension. It's quite low. And then we do it for all 4 dimensions, and we get a similar sharp drop. Then, so we can create the universal gravitational force from that by merely multiplying Newton's gravitational force in parsecs by the circumference, 2 times the circumference, and we get this figure. Now, I have no idea what that figure is, or if it's even anything. It looks to be palindrome kind of number. Maybe it's not anything. Get a lot of shirt jackets and stuff for no reason. It's probably isn't anything. So right, okay. Well, I'll look into that again later on. But so the universal gravitational force, which is the force on the entire it's the force on the entire hypersphere. So it's like checking the surface tension on the surface of the bubble. So that's why we multiply by 2 times the circumference, because that's like the length, and that will give us the force. So that's the force in I'm not entirely sure what the hang on a second.
Recently, Sabina said that gravity is not a force.
Right, but this is well, yeah, I don't know. Well, I mean, you know, it's force, mass times acceleration is a force, and that kind of applies to gravity. And this is a force on the bubble, though. So this is not the gravitational force, because then we can take the universal gravitational force and divide it by Newton's gravitational force to get the relative strengths between the two of them, and it turns out to be 2.3 e to the 16. But I don't know what that is. But so for a single dimension of surface area pressure relative to g, we get 1 e to the 35, which is very close to
Planck.
Not the Planck. It is close to the
inverse of the Planck.
No, it's close to the coupling constants for the fundamental forces. The coupling constant between gravity and electromagnetism. It's close in there, because that would be. Let me just go back to this. See, gravity is 10 to the minus 39, but an electromagnetism is 1 to the minus 3, if you like. So that's the equivalent
alpha or alpha g.
Right. Yeah. So then that becomes 10 to the minus 36, which is fairly close to what we have here, which is 1
inverse of that.
Oh, it's the inverse. Yeah, geez, good point. Yeah. But I think that's okay though, because that's what we're just saying that it's different by an order of 35. Yeah. So I don't think it matters whether it's an inverse or not, does it? Maybe I'm wrong. Maybe I need to rethink this. It's not the inverse though, because if we look at this, this is 10 to the minus 39 with respect to
alpha over alpha g will be close to 10 to a minus 36, 10 to a power plus 36. Alpha over exactly. electromagnetic over the gravity.
Exactly. So that's what we're doing here. So the whole point of this is to try and understand electromagnetism and gravity from the perspective of the forces acting on the hypersphere as a whole. And we seem to get strengths so for a single dimension of the volumetric pressure relative to g, we get 7 times. So it's going to 7 times the amount. For order 4 root volume pressure relative to g, we get 2.32 e to the 36. So it seems good. It seems kind of using these new values is maybe better than what we had before, but it's difficult to know. Inside out pressure. Yeah, here's just more.
Pressure? The plot of the pressure? Is the plot for the pressure?
That pressure is not that plot's not that important, I don't think.
Okay.
Well, I need to fix it. Because I've just come back to this notebook after a very long time. Now that needs to be fixed. That's not right. But what does it need to be fixed to is the question. I'm gonna just mark it down so it doesn't run. Okay. So if we take the volume in kilometers, we get this number. And then if we take the volume in kilometers relative to g, it gives us 1.5 to the 39, which is kind of like what the strong force being relative to the gravitational force is like, but I'm not entirely sure if that's completely accurate. Not entirely sure what's going on here. Is this the circumference as a ratio to the expansion, sort of how much the circumference is expanding, and then we're just converted. So we're multiplying that by g. So this is the force differential as it grows, the universal gravitational force differential. That gives us that, and this is the same thing, but in newtons instead of, or in meters instead of parsecs. So now this one is interesting. We're looking at the amount of substance in the universe. So we take the end result of the force. It's been a long time, multiplied by the volume, divided by, I'm assuming one of these numbers is, what's the name of that constant?
Avogadro?
No, sorry. It's written Boltzmann, is it? Boltzmann. Yeah.
Constant?
So this yeah, exactly.
That's not temperature. That's for temperature, though. Boltzmann constant is temperature.
Right, but we're moving into temperature now.
Okay.
Yeah, we've been working on volume, pressure, and so the next part is temperature and entropy. But
energy over the Boltzmann. Okay.
Yeah, it'll be temperature
energy value. So you have to do the energy value.
Yeah, I would need to revise this to see what the heck is going on properly. But basically what this is saying is that the amount of substance in the universe is, assuming that these two values are correct, and I can't remember where I got them from, I'm assuming one of them is the Boltzmann constant.
Okay, it has to be applied to the energy, not the force.
Okay, well, we'll look into that. Because I'm using a specific equation. Oh, maybe I am using this equation here. So we have the pressure, the volume. So if we go back here,
okay,
we have the pressure. Well, hang on. This is
pressure times.
We have the volume. Now that should be the pressure, shouldn't it? And I think we're using
the pressure. Yeah,
we're using the force.
Should not be the force. Yeah, pressure times volume is the energy. Yeah,
okay,
you get
let's
energy.
go up here and grab the pressure that we had. Ignore that one. So this is the volumetric pressure. So we'll take this one first. So this is quite big. This is the surface area pressure. I guess it makes sense to use the surface area pressure. So we'll just put that in there. Times the volume divided by this number and this number, whatever that is. Right, so it's divided. It's divided by, this number is Boltzmann constant. So Boltzmann constant times 2 point, so, or is the mole gas constant, sorry. And the temperature. So the temperature is what we're looking for. So N is the amount of substance. So my calculation for the amount of substance back then in the universe was this value. And I don't remember how I got that because I lost all my notes during that computer crash I had. So it might be in one of the videos that we've recorded previously, or it could be in a paper I've written. But right now we're just going to have to, and then divided by Avogadro's number. So we get K. So this is the amount of substance in the universe. No. Okay, so this is something anyway. Let's just see what we get.
Yeah, Avogadro is 10 to the power 23, something
Right.
more.
So this
Yeah.
is the 10 to the power. Hang on a sec. You sure?
Avogadro is 10 to the power 23, 6 times 10 to the power 23 or something.
Yeah, it's a
Uh,
6 times 10 to the power of 23. You're right. So what have I
yeah.
got? I've got the same thing. So that's yeah. So that's Avogadro's number, and so this kg here is the temperature. Then I think, if I'm not mistaken. Um, Why are we? Oh yeah, K. So that's K. Oh, hang on a sec.
Mhm.
Looks like it's a bit muddled, doesn't it? Because
Oh, so you divide the gas constant by the Avogadro, you get the Boltzmann constant. Is that
ah,
right?
I think the equation we just looked at was this one. Now this one is throwing in the Avogadro's constant. Just I think it's just checking to see what would happen if we did that. I don't think this number is really that important. So I think the first one is the correct number. So that is temperature for no, excuse me. This I'm going to get rid of the minus sign. So this is the temperature somehow, but that's the temperature. I don't know. Anyway, so there could be problems with this. I probably shouldn't be going through this now because it's not properly fixed, but pretty interesting anyway that we got. Oh, wait a second. We got something out of this, I think. I mean, maybe the temperature should be minus. Now there's absolute pressure, volume, absolute pressure. Yeah, so I'm gonna have to go back and look at that. I think I even left out the temperature and all of that and the entropy work with the Boltzmann constant the last time. I don't think it formed part of the talk or the results I gave because I was dissatisfied with the general conclude the answers and maybe even the formulation. So that's okay. I can go back over it with the new values and see if it comes out a little better, and that'll be good. Okay, so that's the state of play. So now, do you want to go over what we did in
Yeah.
the yeah?
Yeah, I'll briefly go over that, what we
Cool.
discussed.
I'll stop sharing then,
Uh,
and you can share your thing.
yeah. You can put me back on. Okay. Hmm. Let me
Okay, really, yeah.
see that now, right? Okay.
Yeah, it's looking good.
Uh, so I'll just go through briefly the pages we had. Uh, this is thinking aloud. I mean, it's a
Yeah,
basics here, and then we are thinking aloud. So we are not. We are just brainstorming these things about the time because the time aspect is only coming. My OJPS publication showed about the time being a tensor, which means it's about vector and scalar quantities. And right now, my research shows that it should be a rank 6 tensor. So we are trying to figure out what that will mean. Suppose a scalar time t we use, so we don't use the subscripts. The subscripts means that the rank of the sensor. So if you have one subscript, it will refer to a vector rank 1 tensor. If you have two subscripts A and B, that refers to rank 2 sensor, and that will look like this. Rank 1 tensor will look like that, a Bragg matrix. Suppose it varies. We think from Christopher's presentation could be a 4D, 4 hyperdimension. So if we say IJKL, that's 4 dimension, and then the time. is varying in those space time coordinates. So we have a bra, and you can have a ket vector, and then we can get a delta function, uh, bra times the ket vector. So that gives us the vector of the vector matrix of the time in the space, in the four hyperdimension space. Now we can also get a density matrix. The ket times the bra gives the density matrix, and then we'll look at that. It kind of looks like almost like a rank 2 tensor. So if I have subscript A and B for the tensor, that will be a rank 2 tensor. And I have varying IJKL, which is the space for hyperdimension space. So if I vary that, I get this this matrix, which is II, and so on and so forth. We get 4 by 4 matrix. This is what we come up with for rank 2 tensor. Uh, so going over the rank 2 tensor, uh, let me explain this here. So if you are rank 2 tensor time 3D space, start with that. And we want to denote the 3D space XYZ. It's easier to understand probably. So we will have, if you arrange that matrix, we get a 3 by 3 matrix, TXX to TXZ. And then, so if you expand that, I get 3D matrix, 3 by 3 matrix, which is same as 3 square, which means that, the space, 3D space, then, and the rank 2 means that, so you will have then the, so spatial dimension, then we raise to the rank number, which is 2 here. So the space the
Yeah, that's
space number raised to the rank number will give us the total number of elements. So rank 2 tensor, here you can see we have 9 elements, or is 3 squared. So if we extrapolate to rank 6 tensor time with 4D space, we should get 4 to the power 6, which is 4096 matrix elements. So we analyze the
no, 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 no,
hyperdimension space.
no, that's
We
wrong, Adrian.
Yeah.
Rajan,
Huh?
I thought that we later on we figured out that this was wrong, because what you've just written
Yeah.
is you have 6 space or time dimensions to the power of the rank, and the rank was rank 2, so it's 6 to the power of 2, 6
So
by
for
6.
rank 2, yes.
For rank 2,
So
it would
if
be.
you have, yeah.
Oh, if you want
So
rank
let
6,
me
yeah,
re
yeah, that's sorry, yeah.
Yeah. So
Yeah.
if you have, to make it simpler, let's consider rank 2 tensor with 4D for hyperdimension space, HD space. So then we'll have
Or to
number of elements will be matrix elements will be 4 to the power 2, right? And that will be 16 elements.
yeah.
So that is rank 2 tensor. So this tensor we are talking about time. So it's rank 2 time tensor, 4D space. You have 16 elements, which will be 4 by 4 matrix. I think I am putting that somewhere. Uh,
Right. But if you're looking at some sort of 6-dimensional thing, then it's 6 to the power of 2, right?
yeah.
6.
So let's move on. I think we'll look at it later.
We may not have written that down. We probably just spoke about it. I'm not sure.
Yeah, I can write it down again. Okay. So if you have four-dimensional uh, space, let me put here. Okay. So we have this one will look like, let's say, T of U uh, X, T of U Y, oh, U of U, sorry, T of U X, then T of U Y, and T of U Z, and we permitted it up to T Z of U, and then you go all the way up to T Z of Z. This is, you can see this will be a 4 by 4 matrix. So you have 2 Z X T U Y T U Z. So you have 4 by 4 matrix. So essentially, then that will be for the rank 2, and we extend to rank 6. So rank 6 time tensor will be typically T, can be written as A, B, C, D, E, F. So rank 6. And then so T of A, B, C, D, E, F. Then that will be rank 6. And then you have 4D space, which is written as probably X, U, X, Y, Z. So you have that. So when we combine these two, we get. So you said that it should not be 4 to the power 6, right? It's not be,
Yeah, it would be 4 to the power 6.
so it will be 4 to the power 6. So the number of matrix elements will be
But I don't
4 to
think
the
you
power.
want this. Do you want a rank 6 tensor? Maybe you do. That's
Yeah,
4096 elements, I think.
yeah, that's what we are saying. Is
Okay.
it 4 to the power 6 or 6 to the power 4? Let me see.
Well, the rank of the tensor you're saying is 6, and the number of
Yeah.
elements is
So
4.
yeah,
So,
so it will be
or
4
the
to the power
dimension
6.
is 4.
It will be 4 to the power 6. Yeah, because yeah, I mean we found the equation to be, this is the space number. This is the time number dimension. Okay. So that makes sense. So so what we are saying is a rank 6 is almost like a sixth dimensional time, but you cannot really attach a dimension. We say it's a virtual dimension. So rank 6 time tensor will have 6 virtual dimension time. And then we have 4 hyperdimension space. Will have 6 dimensional space. What we are saying is that if we multiply this for HD space times the 6 virtual dimensional time, then we get 24, and that is equal to uh, like a 24 cell configuration of Christopher. I can call it Christopher lattice or
Okay.
space
Did
group.
you know
It's called SL. What is called SL? This is
SL2C as
called
well?
SL2C. Okay.
Okay, yeah. So just move the paper up a bit so we can see what you're writing. Yeah, it's better.
Yeah.
So rank 6 time
Okay.
dimensions, 6 virtual time, 4D space goes to 6-dimensional space. How did you get
We
the
get
4D to 6-dimensional space?
that's what we are. Rank six is six dimensional. No,
Oh,
no,
yeah, yeah, yeah.
4D space, 4D space, and
Okay,
six
but
dimension time.
so the question I have is why are you multiplying 4D space by 60 time to get 24 if above we have
Uh,
4 to the power of 6, which equals 4096 or something?
Elements, yeah. So,
So
but
one is
the
elements and the other is what?
so let's say what is 24 times 24? Let's calculate.
Is it 280? 8?
Oh, 24. Okay.
No,
So
it's probably not
you get
288. Probably a lot more than that.
uh,
Oh,
yeah,
it's a lot more
400
than
something. That will be 400. That will be 24. Yeah, let me find out.
that.
I'm
24
calculating
squared,
the old way.
576.
Let me see. It's 8 and 4, 576. Uh, I'm trying to see how we get 4,000. So that's the 4 to the power 6,
You
right?
get
We,
4,000 because you go 4 to the power of 6 is 4,000
yeah. So
and 96.
if we divide 4,096 divide by 24, what do we get? Um,
I'll tell you now. You got 170.666 to infinity.
oh, that doesn't make sense. So, so we have what we are talking about then is 24 cells. Let me look at that. We got a 24 cell configuration. What does it correspond to? Let me check. Uh, yeah, what we calculated here is the 24 times 6 under 44. That's different. SL2C. So we have to recalculate some other things. So we will try to do that.
Well, I think, yeah, that's sounds interesting. I don't know if we're going to get to the 24 from that. Um, I see what you
Yeah.
mean. Though. I
So
see
that's
what
something we have to
you're
think
trying to
further.
get.
But what we are saying is that we found that from the last discussion, the last video discussion, that uh, we can have 6 universes. So and the video about the spacecraft moving, uh, about somebody's work. What was his name? The,
Oh, it's a Lobachevsky in space.
Laboratory space, yeah. So the space is going through that. The spacecraft is going through that, but only if it's fundamental domain, like Christopher mentioned, that it can pass through that, can transcend to the other space when we reach the speed of light. It has to exceed the speed of light to move out to the other universe. But in our universe that we are talking about, uh, actually, it's an infinite universe. Like the discussion we had, the presentation he had just before, we have infinite. The boundary is infinite. So we can only hypothetically say that the spacecraft somehow is able to transcend that to go to the other universe. Uh, then in that case, the light can wrap around in one universe, and because of uh, the conservation of time that I talk about in the for the tensor in my for JPS publication, I have proved that we can get a conservation of time. That's another topic. So the conservation of time does solve the problem because there is no conservation of momentum like the previous history of physics. So you have proved from The Maxwell was trying to do that, but they couldn't get the momentum conservation because the force is not a constant, things like that. So only the time conservation because of the Planck constant. Uh, Let me write that down. The time conservation. None of the paper I saw. So time conservation law with the time tensor for my OJPS paper 2024. So it will show that we can conserve, suppose T of A B or T of, depending on the rank of the tensor A B C D E F, depending on rank. Uh, we can show that the time in one universe, if time vector is going in clockwise direction, then in one universe, then it can go anti-clockwise in another universe. So because of that, we say if light wraps around, for example, fundamental domain, hypothetically, then wraps around. Then the in one universe they can see the back of the spacecraft.
Okay, yeah, but
Like,
that's true in the video, but it's not really true in reality, yeah.
yeah, may not be true. Yeah, I like may not be true. May not, maybe not true. Maybe or
Well,
not true.
there's no maybe about it. It just definitely isn't true
Yeah, not true
in reality.
in reality. Yeah. Okay. So that's important. So, but hypothetically, then can see back of the aircraft, um, like like Back to the Future movie. Uh, so if light wraps around in fundamental domain, hypothetically, then in another universe, can call it alternate universe, whatever. Uh, they can see friend of the universe, friend of the spacecraft, like forward to the past. Uh, a fiction, fictional movie. Uh, it's like look back
No,
history.
I don't think it is though. I think you're thinking about like a space-time warpage in some sort of fundamental domain, and that's not correct, because we could split the domain anywhere and the light could still go across one boundary to the next. So
our Mobius strip
is the entire universe. Or no, sorry, not the. Sorry, I was thinking about the torus. Is the
may have helical? May have helical.
Sorry, that's a different point. So that's
okay.
That needs to be explained from the beginning.
Okay.
So maybe we should explain that. Will I?
Yeah. Yeah. So we are talking about here, I think somewhere here, right?
Mobius strip.
So then you talk about this is where we look at the Mobius strip. So looking forward, that's true if time is a vector. So we need an umbrella model, which I'm developing, or the physics to develop that. But how that becomes scalar, when it becomes scalar, then obviously time cannot go backwards or anything. So only in the vector time it can go backwards. But what we said was the Mobius strip says that it may not be helical. It may not be the time will not close itself to make it circular. Instead, you have a helical path. So if this is the Mobius strip,
okay, yeah,
you can imagine.
I suppose maybe I will. I'll go over that separately.
You can explain, yeah,
because that's going to confuse people. So is this yeah, okay. So what I'll do is I'll how do I minimize?
Can you explain that, Christopher? Maybe.
Okay, I'll do that.
Go. Okay. And then see how it is like electron and orientation and all that. Yeah.
Okay, I'll do my best. Share the screen. So I think if we look at, go back to this, would this be the best way to look for it, or this is probably better? Getting closer. Oh, the next up is Neil Turok on the simplicity of nature.
Oh yeah. I think I saw that video. I think, yeah.
Okay, here we go. Let me think. Okay, so this is us approaching the speed of light. Yeah, we're getting closer and closer to it, and so this is the time dilation. And then, in order for this to get these results, we have to then once we go beyond the speed of light, you go into imaginary time. And in order for this to work, and then you go two times. So that's 2 times the speed of light. 3 times the speed of light, it begins to go in reverse, if you like. And then we have reverse time, reverse real time, and then we're kind of back to the starting point. But we're not really back to the starting point. But if we think about it on a Mobius strip, so the half twist is the speed of light. So we're here on an untransformed metric, and then we approach the speed of light, and now we're like at a 90-degree angle to ordinary space, so we're flat. And then we move into imaginary time, which is on the inside of the Mobius strip, even though a Mobius strip technically doesn't have an inside or an outside, but just bear with us. But you see that we're going from the speed of light now back down to 0 in a sense. So this is backwards imaginary time. Then the other side of the that's not going to help. This Mobius strip isn't that clear, but the other side here of this side is forwards imaginary time. Then we come out, we're on the back of this strip, and then this is going back to 0. So this is backwards real time. And that is what we see here. Forwards, backwards, imaginary time, forwards, imaginary time, backwards, imaginary time. So once we get to this point, we're traveling, let's say, C, 2C, 3C, 4C. So this will be 5C. So if we go around the Mobius strip, we've already been around once, which was two rotations, a bit like SU2. And then, so if we go around again, now we're at 5C. But, so that's like, the Mobius strip is obviously circular in its rotations, but we are progressing linearly. We have a linear acceleration. So in order to combine the two, we're going to need a helical Mobius strip, which I looked up, and there is no, I don't think it exists.
I don't know whether Rodney Bartlett, he's talking about Mobius strip a lot. I don't know. Do you follow his thing, the Australian? And I think he had a strip, I think, which talks about helical, I think. I'm not sure.
Yeah, I would like a, you know, an image here would be good, but I don't have one. So okay. How does this comport to anything? So is this a helical Mobius strip in a sense? Maybe the other way of looking at it is that it's some sort of fundamental domain that we go, when we cross the boundary of the fundamental domain, which is impossible, but it, you know, so going faster than the speed of light, technically, we might go into a backwards imaginary time, then forwards imaginary time, so crossing again into another fundamental domain, and again, so that's 4 crossings. And the good thing about that, I guess, is you have imaginary time and real time, and different signs of those, but and so then we can talk about complex time as well. So, but where was I going with that? Oh yes, so if we just imagine this as a
Cottonians, you're talking about the Cottonians, right?
That's true, yeah, because this is like we start at 1, then I, then J, then K, and back to 1. So it's quaternions, it's SU2, Pauli matrices, and all that. But if we just imagine that this is a helical Mobius strip because it has we're going on the outside, then the inside. Is that right? And then we're still on the inside, then we go back to the outside again. So this could be like electromagnetism, like a small amount of electricity creates a small amount of magnetism, and that's the whole green thing, creates a small amount of electricity in a sense. So, and then on and on. So it's kind of like light ray, you know, Maxwell kind of thing.
Electromagnetism.
Yeah, and then it kind of, I think it's cool the way it might link in with your work, where it's like
PDP circuit.
Yeah, the PDP circuit, exactly. Sorry, an electron becoming, I think it was like a magnetic monopole, and then another magnetic monopole, the opposite one. So, and then back to
a positron.
Okay, but it seems like the order is out of sync here, because it is positron creates an electron, creates a magnet, one magnet, and then the other magnetic monopole. So that's a bit strange. But if we imagine that this is light, then it seems to suggest, you know, you start at, you go to C, then you go to 2C, 3C, 4C, 5C. And so then it's like light is increasing at every step, its speed. But we know that's not the case. And we discussed that.
Some kind of a torsion or skyrmions or something involved.
Right, yeah. But I know they generally think of light as a planar wave. But if we have this, sequence where it goes C, 2C, 3C, 4C, 5, 6, 7, 8, 9. So it's 9. But then because some of these are going backwards and some of them are going forwards, it seems reasonable that we could just reverse this and lay it over the top. So then we'd have 9 and 1 and 8 and 2. so then you could combine these and get the average, which would be like 5 for all of them. But that's still 5 times the speed of light, you know. And then of course you have other issues such as, well, if this ends at 9 and backwards is the same as forwards, then this could be 9 as well, you know. So it starts at 9 and decreases or something, and that's a problem as well. So the whole thing is
mentioning about how it can cancel each other, feel like a series.
That was what I was attempting to do, to cancel them, and then this idea of a series, yeah. So it's interesting because, like, obviously the longer you make this, the bigger the number is going to get, and so that's going to alter things. Yeah, so I don't think it can be cancelled. I don't think we can extend the helical Mobius strip into a light ray, although it would be cool if we could. Maybe we could use it to describe the magnetic monopoles that stream from the projective point through the hypersphere onto the tangent plane, but that's a long way off. We haven't even really considered that, but it's a possibility. So stuff like that is yeah, I mean, that's a definite possibility. You know, you could start maybe bringing your PDP circuit into that somehow. You know, because those things are generating the particles, and they're also, it's also outside of normal space and time, which is, and it's also superluminal, obviously, because it's instantaneous, and it also
things.
But also more to the point, you know, you could consider it a kind of, how did you think of it before, as a
particle to field
perpetual motion machine?
Become like a
perpetual motion.
Yeah.
Anyway, so I remembered what this was about, Rajan. Just to go back to this, am I on the right? Oh, I am way. So let's go down here. Amount of substance, right? So we weren't trying to figure out the temperature. We were trying to figure out the amount of the substance in the universe. So N. So this was temperature, because that is in Kelvin. That's the microwave background radiation temperature. So K was the amount of substance, like it says there. I should have used N, actually. Maybe I don't want to change it. I might change it later. So this, according to this, the amount of substance in the universe is 1.083 to the 159, which is a fairly big number. So that's pretty cool.
It could be there. It could be there.
Yeah.
We are talking about atoms, right? Atoms, right? Is it atoms?
Yeah, it's difficult to know. Are we talking about galaxies, or I think it's meant to be galaxies, to be honest with you. But even that might be too big, you know. Anyway, we don't know. So then we have absolute pressure. So there's more work to be done on this, but I mean, in a way, we could run this to see what values we get. The other thing that we have to do then is to go over the matrices for SL2Z and check the modular, you know, the modular
universe.
No, yeah, but more these things where we had the lattice, the Lorentz lattice, and then it goes into these descriptions of the lattices. So, because these are just 3x3 ones, so these are modular because they permute, you know. Anyway, so but I don't think we'll do that today, because probably we might have to do that another week. So what's next week, Rajan? Is it
the history of physics, episode 3? Actually, I have the PowerPoint. Do you want to review that PowerPoint? Or should we do it all next? I mean, I have most of it. I have most of it. I may have to edit a few, but if you want to look at it, I can show that PowerPoint how it looks like if you want to.
Okay. Just maybe briefly.
You want to do that?
Yeah,
Yeah,
I'm just
briefly,
going to run this.
what?
Just run through these. Make sure that we got the answers
Yeah,
we
you
need.
complete this one first. Yeah.
Okay. I don't think we need to run any of those. Good. Fine. It's all right. Okay, we're back to where we started. Wait a second. Was this the number we took from the? Yeah, it
Oh,
was.
if you divide by the Avogadro number, I think you get number of moles, I think.
Oh, okay. I think this was it, wasn't it? This was the number we wound up with, so I'm not sure what that is. Maybe that was. Maybe that's the volume of that. That was the volume one, wasn't it? And this was the surface area one.
I think the
So
small nkt or the capital nkt is the n is the moles, I think. Oh,
yeah, you're right.
nRT.
N is the moles. It's the amount of substance. So from a surface area perspective, it's 4.8 to the 100. So let me just check that we have the right values. We want the pressure, but we're taking right. So there's a pressure value for that, and then there was the pressure value for this, which we didn't use. So the other values here are kind of from the previous attempt. So we can replace that. This. I should probably make a note. Volume pressure, and this was surface area pressure. So I think we'll go with surface area pressure anyway, because it just probably makes more sense.
Surface tension is the.
Okay, and we'll check this one. So there we go. Those are the two values. Now we have our absolute pressure volume, which is not, and then we add the last value to all of them. I'm not entirely sure why we do that. Then we reverse it. So we're looking for the force percentage and the so the percentage of pressure. So we're just looking for the percentage, which gives us this curve. Which may also be a percentage of force. Oh yeah, because the pressure. Oh yeah, because you see, you can have the pressure could be a force. So universal gravity. The universal force gravitation thing was, what was the answer? It was this.
Yeah, pressure is a tensor, so it's like stress tensor, very similar to stress tensor. Pressure.
Okay, that comes out at 1.72 to 39, which was, again, a kind of a, so that's the amount of moles. Okay, so we're good on that. Percentage of fine structure constant. So this is the relationship between the pressure and the fine structure constant. Or, well, no, this is just, yeah, this is just to do with how, if there's a relationship between the pressure and the magnetism, then, or the the alpha fine structure constant, then that's going to change as it grows, as the universe grows, because the pressure percentage is growing up to 100% in the first 24-hour period. So fine structure constant would also have to grow in that time. That's the concept here. So now we go
24-hour basis, right? It's a 24-hour basis of the universe.
No, it's not a 24-hour basis. It is a, well, it could be, yeah, but this is literally the first 24 hours of the universe. You know what I mean? So this doesn't repeat or anything.
Yeah.
It only happens with the one time. But then, obviously, after that, how many 24 hours have there been since the beginning of the universe? That is a 24-hour basis. Yeah. That part is true. Where are we now? What are we trying to get? Percentage pressure? I thought we already did that. Oh yeah, but this is from the
percentage fine structure you did.
Yeah, this is the opposite way around. That we're kind of doing it from starting small and then going up. Percentage pressure.
Force increases.
The same thing.
The force is not constant. It's not constant. Force is not constant.
Right.
It's not conserved.
The electric
force is not conserved.
Yeah.
So that's why momentum conservation is not possible. That's one way to look at it.
Maybe, yeah. Absolute volume pressure. Okay, so here we're using the absolute volume pressure, which is, that's okay. How the heck did we get that? Oh, we just added it in. That was clever. Maybe. Yeah, could be clever. Absolute volume. Volume 2 is correct, is it? Oh no, volume is not the... Volume 2 is the actual volume and not the surface area. Could be a problem. Because we were saying we're interested in the surface area. So let's find out the name of that variable so that we can replace it. So up here somewhere. Volume 2, yes, volume was the hypersphere volume, but we want the surface area, which is also a type of volume. And then we get back and here. Hopefully this works. K. Now, what is K? Is the number of moles, or the amount of substance, and then there's the temperature, which we've multiplied by 2 for some reason. I don't know if we need to do that. Also not sure if we need to multiply this by 1 because K.
You're using K as the substance. That's a Boltzmann constant, but that you are using K as the...
Yeah. It's the wrong. It should be N. So let's change
variable.
it to N. Just change it to N. But this might not be a good idea. See, this is volume. That should be volume. I'm going to change that to surface area. I'm going to change this to N.
Yeah, pressure times surface area divided by the...
Okay, so it's very different. It's a different number. There's no need to multiply that by 1, minus 1, because it's not negative.
PV equal to NR, NKT, or N.
Unless G force is negative, this needs to be surface area. So we just check.
And K, you change it to N also, the bottom one, because you changed it.
Yes, very good point. Yeah. G force, we need to check, is this plus or is it positive or minus? It's positive. Okay. G force, though, surface area times pressure, right? So we need absolute pressure volume. I don't think we're using the force on the... It's another way of doing it. Not sure if it's correct. And I don't think we need to multiply the temperature by 2. There might be a reason.
PV or NK will give the temperature. Yeah.
Well, it looks like we're looking for the temperature here. So I'm confused as why.
Capital NKT. Yeah. PV equal to capital NK.
That might be a correction factor. So we'll leave it out for the minute and see what happens. So it starts at 0. This is the temperature gradient of the expanding universe, and it goes to, great, goes to the right value in a sense, although it is minus.
It's reducing. The temperature is reducing.
Yeah, the temperature is reducing. That's not... Although that is right, because if the pressure is reducing, the temperature would be also reducing. Here's the temperature is going up. Oh, so that's the correction factor. The put the correction factor back in, plus this.
And increasing entropy.
Now it goes down. Right. So 2 times, didn't we say was the correction factor?
How does the entropy change, right?
Exactly. Right, so there we go. So it starts at this and drops to the value that we see today. Okay, so how does the entropy change? That's what we're going to check next. So, so if this is the temperature, then this is the entropy. And then that's it. We're done. Okay.
No, temperature entropy increases, temperature goes down.
I don't know.
I thought they are directly related. I thought entropy increases, temperature also increases, isn't it?
Right. Yes, but this is a Legendre.
Temperature.
This is a Legendre transform. So
temperature
you have to flip it. So as the volume increases, the entropy increases. As the volume increases, the temperature decreases. So the temperature is going down, the entropy is going up. Correct?
I thought temperature is a measure of entropy, right? It's the gradient, whatever. Because the definition. Okay, it's a heat. Entropy is defined as heat over temperature.
Okay, all right. That's maybe another way of looking at it. Well, this is entropy in
delta
terms of
Q over T.
You know, these are just right. So the entropy should be the entropy should be increasing. So technically, at the start it should be like really low, like maybe 2 or something, or 1, 0. I mean, and then it goes up. But this is only up until the start of the universe at 24 hours, so it's still quite low. And there may not actually be any material in the universe within the first 24 hours. So this is this is just kind of applying the maths to see what results we get. But in a sense,
then
later work revealed that, well, maybe there wasn't any matter there to begin with. So that's a possibility. So that's kind of it for today. Unless you want to, will we sign off? Sign off. My throat's getting.
Do you want me to review? Want me to review that, or do you want me to
maybe review it off air or something, so you don't
the history, the next week's episode? Do you want me to review that?
I'm just thinking maybe to do it. We can just sign off, and you can.
Okay.
Yeah.
Oh, you don't want to put it here. Anyway,
well, because what's the point in putting it
next
here?
Week.
Yeah, exactly.
Next week, we are going to present it anyway. Yeah, that's fine.
Yeah.
Just to clarify, the entropy S is delta Q over T. Yeah. So
entropy.
So I'll just review
delta
that.
Q, which is what
over
heat,
Q.
The difference in the heat.
Change the
change in the heat divided by the temperature.
Over the temperature.
Sorry, you roboted out there. I couldn't hear you.
Absolute temperature. Yeah.
So the delta of the heat divided by the absolute temperature. Well, what is the absolute temperature of space? Is that the Kelvin thing?
Yeah.
And that's the entropy,
Kelvin.
yes.
The Kelvin.
Okay.
Temperature
so
Kelvin.
In the equation we don't have the heat. We do have the temperature, but it's okay. So let's say we have the temperature.
It works. So that makes sense. So that's how you got The inverse of temperature means the temperature is decreasing, that entropy should increase. Delta Q is constant, So that's how you probably got it, how the entropy increases.
Oh, okay. Well, the entropy has to increase
Maybe.
with time anyway, doesn't it? So we start with a low entropy and it increases with time.
Yes.
When we have
Second law.
something
Yeah.
pressurized in a small area and then we increase the area, the temperature is going to go down as well. So that makes sense. We could work out the heat though with the equation you just gave me, because entropy times the absolute temperature should give the delta of the heat, right? So we could multiply the absolute temperature. Well, I'm not entirely sure what the absolute temperature is, but okay, Rajan, I might. I don't know if I'll take a quick break and we could come back to this. Or,
we can take it. Yeah,
that sounds good. That's a
sounds
compromise.
Good. Thank you. Thank you.
I'm just gonna.
Yeah, we'll just start. Are you there already, Christopher?
Yeah, I'm here. I was
Okay.
trying to get out for a wee walk. It's a very
Okay. Uh,
was trying to get out for a wee walk because it was this nice light rain falling earlier.
oh,
And I was
really?
like,
Oh,
oh, it was just like a misty drizzle. So I was like, oh, that seems really cool. But as
oh.
you
That
can
is
probably
rain.
wait, as you can probably hear in the background now, it's transitioned into quite heavy rain. So
Oh,
it's more just still nice, but it's not as kind of interesting.
ah.
So yeah,
Does
so
it rain? Does it rain a lot there?
yeah, rains yeah quite a bit.
Okay.
Wouldn't be like uncommon for it to rain or anything. Yeah.
Yeah, here I think the temperature it was very hot last week. Then it's going to cool down a little bit. So it's kind of
Oh,
fluctuating quite a lot.
are you near Las
Kind of like
Vegas?
summer. Yeah, we are not too far, but I am Arizona, which is a desert, the
It's a
Phoenix
different
area.
state, isn't it? Las Vegas, Arizona. No.
No, it's like Arizona. Las Vegas is another state.
Oh, is it?
Nevada. It's part of Nevada. Yeah, it's
Ah,
another state called Nevada.
oh,
Nevada.
right, right, right. I was wondering if I got it completely wrong or not. Different state. Gotcha.
Yeah, yeah, that's it.
Oh, of
Then
course,
California. Yeah,
Reno,
we
Nevada.
border those states. Yeah,
Yeah, I'm not too familiar with my geography around that area.
yeah.
But
It's a lot of.
so what have you got there? You got Area 51? No, that's Las Vegas as well, isn't it?
Yeah,
That's
it's off of
Nevada.
that. I'm not complete. I think it's border between Nevada and some other state. Which state it is? Not New Mexico. It's another state. I had to check that. You can check that. Area 51 is off of
Yeah, that's
Nevada.
in Nevada. It probably borders another state, like you said.
Yeah, yeah. I thought it's
Possibly,
in New Mexico. I'm not sure.
would it New Mexico or maybe wouldn't border California, would it?
I don't think so.
Don't think
Let
so.
me
It's a
check.
bit too far away, is it?
Yeah. So it would
Yeah,
be, let's see, Area 51. Let me see. No. Yeah, it's part of Nevada called Groom Lake, Nevada. Um,
oh,
Groom Lake, Nevada. Groom Lake, Groom Lake, Nevada, which is a dry lake. It's a salt flat, Nevada, used by the Air Force, like Air Force base. Yeah.
uh-huh.
Uh, yeah, so that seems. Let me find our area. Yeah. We did the border other states. Um, wherever they say area of given aliens and the truth
What does it
of
say?
southern Nevada. 100 miles from the Las Vegas area. It is this off. It's a little bit further than Las Vegas. Uh,
Yes.
they don't say any other state. Let's look at the map. I don't see the map here. Showing the map. And we have to
You pull up the map, or
use map.
this is riveting television here.
Yeah.
uh,
Okay. So made it. So this is the image. See if I can. So if I go there, you see the map. You have
yeah.
that. It's above California. This is California. So it's Nevada here. So you're right.
Nice.
And
Nice.
then,
Yeah, Death Valley,
yeah, it is. You can go from California actually. Go up. This is where it is.
Oh,
Uh,
so where's Las Vegas
Area
there?
51. Yeah, it's right here, Las Vegas.
Where
Area
are
51.
you? You're
So
just
this is
over the next.
Nevada.
The California is huge, actually.
Yeah. I can look at that one. Yeah, it's quite huge. Called Nevada. That's right. Mm. Yeah, it's above California in Nevada. It's actually closer. Yeah, it's in Nevada. Las Vegas is somewhere above there. So Death Valley. This is a Death Valley in California. So it connects with that, I think. Somehow.
Well, that makes sense.
Somewhere in that region. Yeah. So Arizona is
Oh,
way down here. Yeah. So that
uh-huh.
you are bordering California and Nevada also. Arizona borders Nevada.
All right.
And then you are Oregon, Idaho. So this is it's quite interesting.
We got test
I mean,
sites
there are
there.
a lot of studies people are done. Quite interesting. You know. So that's it. So you want me to show the next week's thing?
What do you think? I mean, you could probably save it for next week, could you? Just
Yeah,
so
I
it's
can.
yeah.
Yeah,
What you can do
mostly I
is
have.
we could. I suppose you could email it to me or something. You could look at it that way.
Or we can just look at it quite quickly now, and you can see if there is any.
Okay. Well. Okay. Well. So, do you want to end the stream? So.
Yeah, you want to end the stream and then just review it,
Okay, yeah, it's fine.
and then if there is it's generally okay. Then I may edit a little bit, but I think mostly I'm going to present that.
Okay,
That's
fair enough.
possible.